Hi, everyone. My name is Shan. I'm from the Uber visualization team. We are a team of 30 people for now, so a big team with a lot of data visualization specialists. Today, I will be talking about this geospatial visualization tool that we built in the team. It's for exploring and visualizing large-scale geospatial data in your browser, and it's called Kepler.gl. So I will be talking a little about why did we build this tool and how do we build it. And then if you haven't heard about it, we're actually going to open source it in the next month or so. So stay tuned. Today, just a preview. At Uber, we are handling millions of geospatial data every day. It is one of our biggest assets. Every day we are doing millions of trips everywhere. And then every single moment that we're not utilizing or studying those trips and those data, we miss on the chances to make our operation better. So at the data visualization team, we make a lot of maps. Since I joined Uber, I would say 4 years from now, I have made hundreds of thousands of maps. And then sometimes, if you count the maps I made to the stock I should have, I'll probably be rich. So sometimes, at one point of my journey at Uber, I started thinking about this. Why do I make all these maps? I love my jobs. I always be able to draw something on the screen and it looks fancy. But at the end of the day, what I really hate the most is someone come to me, saying, hey, I really like the work you did. Can I use it as my screensaver? So at that point, I just felt like, as an engineer, I wish I could do something more than just putting pretty pictures on people's screen. So as a visualization team, we make maps so that we can gain insights from the data. And then we do a lot of this practice every day, and then we can tell you the process can be painful. So in theory, if you look over the shoulder of any visualization person, they always have something nice on their screen. So you think like, okay, this is what they do. They write some code, they use this compile, it runs, and then you just show things that looks pretty and look nice. But in reality, it's more like this. I think every coder here probably understand what it means when you just have errors in your terminal for the entire day. So this is also the same for us too. The process of making a map visualization, you have all these 4 steps you have to go through every day. You draw some sketch, you create some mockups, you build some prototype, and then in the end, you make it to production. And the more of the times you actually got stuck in this infinite loop where you just always have to go back to your drawing board, change your process, and hope you get something that's meaningful. An example I want to demo of this whole process of making a meaningful map, I want to talk about the story the visualization I did for UberPOOL. So the idea of UberPOOL is very easy. It's simple. You have 2 people riding separately, and then instead of having them ride separately, you will send 1 car to pick up both of them. In this case, instead of doing 2 separate trips, we actually have just 1 trip happening with 2 people stuck into 1 car. And then ideally, if you choose UberPOOL, you will have less cars on the road. So the hypothesis is very simple. And then I have all this data that UberPOOL trips. I want to make a visualization that actually can help me tell the story, can help me prove that this is the point behind UberPOOL. So I took those data, I go back to my computer, I start this journey. I did many tries, I used many different tools. If you do visualization, you use D3 or use Python to do data processing, or if you're a GIS specialist, you use QGIS. So first time try, all I did is just brutally throwing everything on the canvas. I draw all the passes of all the trips on the single map. And I was hoping, there's some kind of, density, opacity could show to tell me that how the how many cars on the road. But it's not very ideal. So I went on to the second try. Instead of drawing passes, I started drawing just the raw GPS points. I piled up all the points on 1 single map. I still don't see a pattern. And for my third try, I go back to my drawing board. I was thinking, okay, what is the most important thing about traffic? That is the volume of cars on the road. So what if I actually calculate the volume of cars on each street segments and use colors to indicate traffic? This is like kind of what I just need to do. And then the result seems more promising than the first two. And I also, as I'm always an animator, I made this animation, animating 1 day of UberPOOL trip, color the trips by traffic, and then compare to separate trips. For the comparison, what I did is that I simulated 2 separate trips for each single UberPOOL, and then I calculate traffics on each row segment, and then convert them back to colors. So as you can see, there are many different steps going into creating this visualization. It took me 2 weeks. I used all different tools. I tried many times. And then in the end, I was able to get something that's very promising. But it's 2 weeks of my time, and how many of 2 weeks do I have here? You know, job security aside, I want to have like a better process. I want to improve this process for every single visualization specialist, so that this kind of journey will be easier for them. So I go back to thinking about the common process of doing geospatial visualizations. You get some data sets, you do some data processing, you filter them, you clean them up, you're formatting them the way you want. And then you try to play around with colors, with dimensions, just so that each of single data point convert to some visual elements that you can represent on the map. Then in the end, you create a series of visualizations. This is a common step that we're doing every day. So what if we change it? We make an application that can help us go through these steps easily without have to, you know, writing plain JavaScript or writing plain Python code from time to time. So that's the birth idea of Kepler.gl. We built Kepler.gl to fast visualize and fast exploration of millions of geospatial data points in the browser. It's a very Photoshop-like looking like apps. You get this panel on the side to help you customize the visual representation of your data. You can upload any geospatial data set like CSVs or GeoJSON. Okay. And it has this set of preset mapping visualization layers like GeoJSON, a scatter plot, heat map, can help you fast explore between all different type of visual techniques. And then it also does client-side aggregation on the fly, so you can calculate heat maps, calculate hexabins. And then because it's built with WebGL, it's very performance-oriented, and it can do. We defer some of the geospatial calculation into the web shader code that runs on your GPU. And then the basic flow will just be you have some data, you use Kepler.gl, we provide you a set of filters, and then we provide you a set of layers for you to configure your visualization. And then because it have this Photoshop like layer encoding system, so with many powerful configurations that it applies, changing colors, changing sizes, you're able to just explore with your data to see what's really in there. And then you can create many different types of visualization with just one single data set. So I'm going to demo using it. So bear with me, I actually made the demos beforehand just because I'm not comfortable with using Zoom video conference. But it works, so don't worry. So there are a couple of steps you do geospatial visualization as I talk about. You upload some data set to the application, you filter based on your what's in your data set, and then you interact with it, you create layers. So this will be the 5 items that I demo in So first, uploading data. So Kepler.gl accept CSVs or GeoJSON, and we also plan to accept KMLs and shapefile. And then this is a sample data trips they got for San Francisco. I got about 200,000 trips. And each of the row is one single trips. And then you can see that you have some metadata. You have a timestamp looking column. You have some geopoint looking column where this one says begin trip latitude and begin trip longitude. Each of the point pairs tells you where the trip actually begins. And then you have some metadata column like trip fares or time or distance. So this is just one CSV looking table. What I did is that I opened Kepler, I jog it into this upload data dialog, and then it will just take the data, it will process it. Because it has this automatic built-in layer detection, it recognizes that I have this begin trip lat and begin trip long in my data. So it automatically draws this point layer. So right now, this point layer is showing all the begin points of the trip. And then it also find this drop-off point and then show this drop-off layer. And with the layer configuration, I was able to change the color of my point. I was able to change the size of it. And then, just to make it more themographic, I add the additive blending so that, the density shows up by lighting up the whole street. And bear in mind, this is about 200,000 trips that are uploaded. Each of the trips, I'm drawing 2 points. So I'm drawing 400,000 points in the browser. And then you can zoom in and zoom out pretty smoothly. And this is like you can see the whole Bay Area just light up. And after that, once I upload data, I was able to see them by creating all these layers. The next thing I want to do is that I actually want to filter down to a certain time point, because I don't want to just see raw data. I want actually looking for trends. I want to looking for signals I want to find. With that, Kepler does come with this preset filters you can apply to whatever column you have in your data set. It detects the type of data you have. So for example, if you have a timestamp column, it will allow you to draw like a time filter on the data set. So here I am with my 2 layers, one showing begin trips, one showing drop off. I add a time slider. So this will automatically draw like a histogram showing me the distribution of all my trips. And then I make it to be a time playback, actually drag on it to narrow it to a smaller window. Right now, I'm only looking at trips that begin in the morning. So the darkness of the map doesn't really help here. But you can see like the begin trips point is in blue, and then the drop, oh, great, thank you. And the drop-offs are in yellow. And because I'm only looking at trips that are happening in the morning, it's very clear that where you can see this whole financial district and Soma light up with yellow, because that's where most people go in the morning. And then the surrounding area like Marina, Nob Hill are in blue, because that's where most people left work. And I can also add it with this time playback so that it goes through the entire day. And then I can see how it changes throughout the day where the trips actually begin and ended. And then at this point, I stop my animation because this is the evening time, evening windows. You can see the trips are around 8 p.m. to 5 p.m. to 8 p.m. And then the pattern completely reversed, where the yellows are all around Marina and Nob Hill, because where people go. And then the blues are around Soma and Financial District. And I can do a free drag on my time slider just so that I can compare between different times. And the next step, after I was able to, adding filters to it, I want to also closely interact with every single data points. You know, I don't want to just show a map like a static image. I want to be able to actually zoom into very low level, hover over each point to see what they are. And I want to interact in a way that I can actually highlighting them based on my mouse location. So with Kepler, we have this interaction called brushing. What brush does is that, actually, let me go back. I created a layer called arc. An arc layer will link 2 points. In this case, I use an arc to link between the begin and end of the trips. And then you can see when it first started, it goes crazy because there are 200,000 arcs. I changed the stroke to be thinner. I also start to play around with the color. I want my arc, the start and end of the arc look differently. And also I'm very specific about colors. I actually change a lot just to get the one I want. So in the end, I think blue and orange is a good pair. So now the start of my arc is in the bluish and then the end is in orange. You can kind of already see there are different hops kind of linking to each other, but this is still quite a lot. There's still 200 trips happening there, and then I can't really see where the patterns are. So that's why we have this interaction called brushing. What brushing does is that it will only highlight trips, a start and the arcs, a start and end around my mouse location. So I can change the radius of my brush just so that based on different city, I want the resolution to be different. Now it's at 1.5 kilometers in radius. And as I mouse over the map, I was able to only see trips that start and end around a specific location. So this is very interesting. Actually, you see me trying to look for SFO. Like, where is it? Where is it? There you go. So once you find it, you see because a lot of trips start and end around SFO, and then you can see the pattern of where different part of city connects to each other. And then obviously most of the trips are still around downtown, but then once you look at the airport, you know, you see the volume changes. So because we don't want you to just see it, I mean, with interaction, we actually want people to be able to play around with what is on their map. And last but not least, so far we have been only showing each individual elements. We're showing each individual trip started, each individual arcs. A lot of geospatial operation, what we want to do is actually the aggregated trends of the entire region you're looking at. So Kepler.gl have this on-the-fly aggregation function. Certain layers that it provide actually have this aggregation function. For example, a heat map, a hex bin, and a grid layer was able to aggregate based on each individual raw points. So here I'm demoing changing this point layer into a hex bin layer. So a hex bin layer will aggregate based on all the points I have, and then draw this just draw this heat map-ish kind of layer showing where the density is. And I was able to just change the radius of my hex bin just so that I get it more fine grain. And again, I'm really specific about colors. So I kind of wanted something more pinkish in this sense. After I changed the color, I also changed the scale, how my color is based on. Right now, it was based on quantile, and then I changed it to quantize, which is a more linear distribution of calculating color. After I changed it to quantize, I kind of already see where the outlier is, where the high density area is. And we also have a kind of really fancy operation on it. Although a lot of people telling you don't do 3D maps, but you know, why not? So we add a third dimension to our hexagon. We're able to draw the height of each hexagon based on the density. And once you add like a third dimension to it, you can already immediately see where the outlier is, which is around the airport because that's where a lot of trips started. And I also changed the cover of my hexagon to be thinner, so I was able to see what's actually under it. So when we have all these really high outliers, a common practice is that we want to hide them So we make the pattern of the lower percentile element more visible. So we built in this brush called percentile brush, which allow you to only narrow down to a lower kind of percentile element and then recalculate the color. So you kind of see the patterns around. Right now, this is downtown SFO more visible. And in the end, because we're going to open source it, we realize not everyone have trick data. So we want to provide a more generic tool. So for people, whoever have different type of geospatial data set can use it. So we also have this geometry layers, which is more generic to an everyday geospatial data analysis. We were able to draw process GeoJSONs or well-known text file and just auto-detect geometries with it. So this is me. I found a SF contour GeoJSON file. I just drag into Kepler. And because this GeoJSON contains about 13,000 of contour lines, all shaped in a line string, Kepler finds it and draws this contour line layer. And then I started to customize it because, I like play around with colors. So what I did is that I changed the stroke to be thinner. Oh, actually, I started by color the contour lines by actual elevation. So because it's a contour map, you can tell after you color them by elevation, you are able to see where the higher part of SF is. And then I change it to a more, fire and heat, fire and ice color scheme. So the actual lower part show up like more purple-ish. And then because we have filters, I started to filter on the actual elevation. I just randomly started to drag on the filters. So I see like the lower kind of only showing contours of the lower elevation. We're only showing contours of the higher elevation. And with that view, you can see where the actual higher point of SF is by just this simple interaction. And some additional features, which I will not go into too much detail, is that we do have many different maps. So right now, all the maps are dark, but we actually have light scheme maps just so that, when you do a presentation, it shows up better. And we're also able to actually, so right now what I did is that I dragged the label of the base map. I have them showing on top of my contour lines, so you can see where a different part of city actually is. And some additional, we actually also integrated with building, 3D building backend. So we can actually requesting building meshes on the fly. And then we also were able to draw 3D, 3D, why not 3D polygon layers. So that's all the demos. And because people here are all coders, let's talk a little bit about the tech stack and architecture, and then the packaging and open source effort. So Kepler.gl is built with four simple elements. It is a React and Redux app. It is based on Mapbox.gl, which is an awesome WebGL-based mapping library. And at Uber, we also write our own libraries, React Map.gl and Deck.gl. Okay, I didn't want to jump into that too fast, but. So those are the four key components that Kepler is built on top of. React Map.gl is actually an awesome React library that actually is a simple wrapper for Mapbox.gl. And then Deck.gl is also one of our open source library that renders WebGL-based map, high-performance map visualization layers on top of your base map. So, okay, what's up with all the GLs? I probably already threw 5 of them in front of you. And then just to add another one to sweeten the deal, we're going to also name Kepler.gl. So, I mean, it's kind of obvious everything is based on WebGL, right? But where are all the other pieces and how do they come together? So if you want to build a high performance map on your browser, you definitely need WebGL. And then to render a map with WebGL in your browser, this is open source library called Mapbox.gl. Mapbox.gl is a high performance library that help you render maps in your browser. And then because a visualization team, we would do a lot of React-based applications. We do a lot of map visualizations. We create our own suites of visualization library, which complements Mapbox.gl that help us build high-performance React-based mapping visualizations. So a basic WebGL-based map visualization application, look at this. You have your base map, which is rendered with Mapbox.gl and React Map.gl. And then you have your visualization layers on top of that, which is handled by Deck.gl. Deck.gl has this layer manager that that comes with a suite of basic layers that you can play around, or you can write your own Deck.gl layer. And then under the hood, Deck.gl will sync with Map.gl so that your visualization overlay fits perfectly on top of your base map. So Kepler.gl take this whole mapping stack, and then it adds this filter components, it adds the layer configuration component to that, just so that you can just take any data, do the filtering, do the configuration, all in just one single app. So we are very performance oriented, as you can see. It's all about performance. So some of the tricks we do with performance, actually there's a lot, but today I will just talk one thing, is that we're actually handling map projection and some of the mouse interaction in the GPU. What it means is that, there are two rendering engines, there are CPUs and GPUs. WebGL is all GPU based. But why is rendering things in GPU so much faster in CPU? And if you're doing a simple calculation called project, you want to project a couple of points, geospatial points onto your screen. So you need to call this function called project. And then your CPU will take this array of points and then call the project on each of them one by one, and then to get the string coordinates for all of them. But since GPU is parallel computing, you were able to do all of them in parallel. And then as you can imagine, if I have 200,000 points, obviously doing project on my GPU side will be a lot more performance. The only thing is that, doing things in CPU, most of the things you do is you write JavaScript. And this plain old JavaScript looks so much familiar. You do a points filter and do any calculations. But when you do things with GPU, or you need to write this type of things called GLSL shaders. GLSL shaders is a sort of set of things that WebGL use to tell your GPU how to render your points. This is a simple shader code that I write in Kepler just to do the mouse brushing. So what I did is that for each of the point, I take a mouse position and I do this calculation to determine whether this point is in my mouse range. And then I use that result to calculate the radius. By doing that, I was able to do this kind of interactions. It will be impossible to do that with just JavaScript and then do the calculation on your CPU. And in the end, packaging and open source, because we built this tool and a lot of people like it, and then they want to use it, but we have done a lot of iteration on it. Kepler was born as a single page Redux app. We did 2 major refactor on it. We did 3 UI redesign, and then we upgraded Deck.gl 4 times, all in the course of 2 years. And right now, it's a very powerful geospatial visualization tool. A lot of people in Uber like it. Many different teams want to use it in different ways. Hence, we got many possibilities, aka feature requests. Sometimes people say, "Oh, can we render like a chart panel on the side?" Sometimes they're like, "Can we export a video with it?" And some people ask, can we render 2 of them in just one app? And as the feature requests piled up, we realized that we just cannot simply just add features to our package because we want to keep Kepler.gl just one single core functionality very good. And then all the different interactions or specific use cases should be built outside Kepler.gl. So what we decided to do is that we want to package Kepler core, this core interaction, filter, layering, interaction into just one single package. And then different web applications can take this package and build on top of it. So that's the idea behind packaging Kepler.gl. The currently Kepler.gl package includes a set of React components that include map containers, set panel, bottom widgets, models, and a set of reducers that handles the data binding, the rendering, the map rendering. And then a set of utils that has like data processors, schema management, file handling, and exports. So if you want to build an app with Kepler.gl, all you need to do is you need to add Kepler.gl reducer to your reducer and then add Kepler.gl components. Under the hood, the Kepler.gl reducer will know to find the components, and the components will, sorry, the other way. The components will know to find the reducer to get the state of it. And then there's some code snippet where you mount Kepler.gl reducer in your root reducer, and then you mount Kepler.gl components in your app components. This all seems easy until we realize, okay, what if we want to render multiple Kepler.gl in one app? It's a legitimate use cases. And then if you know anything about reducer, you will know like if you have multiple instances of components in your app, you need multiple instances of reducers. So what we did is that we have this big Kepler.gl reducer wrapper, which will map adding an instance of it, Kepler reducer inside of it, mapping it to the components, and then do some forward dispatch on that. So each of the component will know which reducer to call action upon. And in the end, we also have this dependency injection system because Kepler.gl is like a giant component that has couple, 40, 50 different smaller components under the hood. And the use case always come to us, like, for example, someone say, I want to render the map popover just a little bit different. And how do we do that? Because there's only one single entrance to your components. And if you do the React way, you have some props there in Kepler.gl saying custom map components, and then you pass it in, and then you pass it all the way down to the map popover. But this is not scalable because we have hundreds of components. We cannot just create hundreds of props on Kepler.gl just so that you render things differently. So what we did is that we designed this dependency injection system. We allow you to just swap out one of the components without actually have to pass it at the bottom of Kepler.gl. All you need to do is that we call this function called inject components, which will take a custom components and then call upon this inject app injectors to just so that it returns a new Kepler.gl instance and render a different map components. And then if you want to actually adding a different props to it, we have this with state helper, which is basically another form of connect to help you to get more different props into your custom components. I think, yeah, that's all about the architecture and the open sourcing part. And in the end, we're open sourcing Kepler.gl in April. So if you want to do beta testing, remember this link or just go to this link, submit a form. We will contact you for testing. Thank you.